morning everyone. So, whatever we are doing in last few classes, we are looking into the solution of transient heat conduction problem, or in general you can convert all the analysis into any transient transport phenomena problem, right. Whether it is a heat conduction or whether it is a fluid mechanics problem, it really does not matter, because the way we have looked into the solution of various forms of equations with several boundary conditions, all sorts of boundary conditions probably we have encountered. The solution technique was really in general. Okay. So, not necessarily our analysis is valid for the transient heat conduction problem, it is valid as well for any other transient transport processes. Now, whatever we have done till now is basically 2-dimensional or 3-dimensional conduction problems in planar coordinate. Now, in a typical for the applications of typical chemical engineering problems, the coordinate system may not be well defined Cartesian coordinate system. It may be circular polar coordinates like flow through a tube, right, or if you are considering a nuclear fuel element, it is a cylindrical element, right. In any nuclear application, it is a cylindrical fuel element where you would like to find out the heat that is transported from the center towards the radius. Okay. The amount of heat that is transported from the center to the radius will be taken up by the coolant liquid. Okay. That is a typical fuel element in nuclear reactor. Okay. So, or there may be several other applications as well. So, it is very important to look into the transient conduction or transient analysis of the cylindrical coordinate. Okay. So, in the first problem that will be taken up will be the transient heat conduction problem. Problem in one dimension. That means one dimension and time. So, it is basically a two variable problem. Now, if you look into the governing equation, the equation looks something like this. The form of the governing equation is del u del t is equal to 1 over r del r del u del r. It is basically a solid cylindrical element, and you would like to find out what will be the temperature profile between the radius r equal to 0 and r equal to 1, as well as a function of time. Okay. Now, u is basically your non-dimensional temperature, okay, and there will be some constant will be appearing here, alpha k by rho Cp, that will be incorporated into the time varying part that we have seen in the last class formulation. So, I am just considering the alpha equal to 1 for this problem, it really does not matter. Okay. So, the typical initial condition is at time t equal to 0, u is equal to, it may be some prescribed function of radius which will be a function of radial location, or it may be constant. Okay. Now, you require two boundary conditions on u to solve this problem. The typical first boundary condition will be at r equal to 1, that will be r equal to 1 means at the surface. Okay, at the surface, let us say u is equal to 0, that means at the surface T is equal to some prescribed temperature Ts. Now, if you change the shift the temperature axis, let us say theta is u is equal to T minus Ts, then that boundary condition becomes homogeneous. Okay. Now, the domain of R is basically from 0 to 1, right. So, we define a boundary condition on r equal to 1, that is u is equal to 0. So, we have to define a boundary condition on r equal to 0. At r equal to 0, it is basically a central line. Okay. This is r equal to 0, this is r equal to 1. So, at r equal to 0, it is a central line temperature. So, T is equal to some temperature, it must be assuming some finite temperature, right. So, we write it T finite, we really do not know what is the value of this T finite. Okay. So, this is basically u is equal to some finite value of temperature at that point, but we really do not know the value of the temperature there. Okay. So, any boundary condition for solution of a given equation, the boundary conditions must be known, otherwise you cannot solve the problem. So, we call it is a bounded solution. The value of u is bounded there, that means it is finite, and we really do not know the value of that value of the temperature at that location r equal to 0. This is a typical example of physical boundary conditions that we are discussing in the very first class. This is a typical example of a physical boundary condition that we are discussing in the first class, and this boundary condition comes from the physics of the problem. Okay. Now, since this is the governing equation is linear, you can use the separation of variable. No, you should have come earlier, means we should start the class. No. So, we define that u is a function of a time varying part and radial position varying part only. Okay. Now, if you substitute in a governing equation of your heat conduction, then it becomes r dt is equal to T by r d dr r dr. Okay. Now, you can separate the variables. It should come 1 by T dt is 1 over r dr r dr. Now, the left hand side is purely a function of time only, and the right hand side is purely a function of r only, and they are equal, and they should be equal to some constant. Okay. Now, again this constant can be positive, this constant can be 0, this constant can be positive, this constant can be negative. Now, there is a slight difference of this case compared to the case that we have considered in the Cartesian coordinate. Now, let us examine each of these cases when this constant assumes values 0, positive or negative. Now, this constant is 0, that means we look into the radial variation 1 by r d dr r dr is equal to 0. So, that means d dr of r dr equal to 0. Okay. That means r dr is equal to a constant, right. Is equal to constant, let us say it is a C1 and dr is C1 by r, right. One more integration will give you r is a function of radius, that is C1 by r plus another constant, integration constant C2, sorry C1 ln r plus C2, right. Now, r varying part must be satisfying the boundary conditions of the original problem in the r direction. That means, at r equal to 0, your r is finite, and at r equal to 1, your capital R is equal to 0. No? Okay. Now, whenever you will be putting the value, the boundary condition, when you will be applying the boundary condition at r equal to 0, these terms blows off. Okay. That means, the r becomes infinite at that boundary r equal to 0, okay, which is not matching the really boundary condition that is the existing on that particular boundary. Okay. So, the associated constant has to vanish. Application of this boundary condition means r becomes infinite, which is not the case in practice. So, the associated constant must be going off. So, C1 will be equal to 0. So, r equal to 0 means it is a constant, right. Now, we apply the other boundary condition, that is at r equal to capital R, at the small r equal to 1, your capital R equal to 0. That means, your C2 will be equal to 0, right. So, C2 equal to 0 if you apply the other boundary condition. So, the whole solution becomes 0. So, you are again landing into a trivial solution. So, this gives you a trivial solution. That means the constant cannot be equal to 0. Okay. Now, let us look into the other options. The constant is positive, let us say it is lambda square. Okay. So, the r varying part becomes 1 by r r d dr r dr dr is equal to lambda square. So, it becomes d dr of r dr dr minus lambda square r r is equal to 0. Okay. Now, you define a change of scale of radial coordinate, let us say y is equal to lambda r. Okay. So, let us say what it is, this equation becomes r d2r dr square plus dr dr minus lambda square r r, right. Now, we express smaller in terms of y, and let us see what we get. Dr dr is nothing but dr dy dr. So, what is dy dr? It is lambda. Lambda is a constant. So, lambda dr dy. One more differentiation, it is basically lambda d dr of dr dy. So, again using the chain rule, d dy of dr dy dy dr, again dy dr is lambda. So, it becomes lambda square d2r dy square, right. Then you replace lambda r as y here, and let us see what it looks like. So, basically it is nothing, you just have a shift of scale of small r. So, you defined y is equal to lambda r. Okay. Depending on lambda is a fraction, then it will be a contraction. If lambda is not a fraction greater than 1, then it will be extension, stretching of the axis of the scale. So, let us say r is nothing but y by lambda, that is the first term. Small r is nothing but y by lambda, and d2r dr square, d2r dr square is lambda square d2r dy square, right, plus dr dr is nothing but lambda dr dy minus lambda y r is equal to 0, right. So, this becomes y d2r dy square plus dr dy minus y r is equal to 0, right. What is this equation? This equation is known as the Bessel's equation of the second kind. Probably you will be come across this equation in one of your mathematics course. Already you must have done or must be doing sometime in your future. The Bessel equation of second kind, and it constitutes the solution of Bessel functions of second kind, that is 0th order of Bessel second kind of 0th order. This is 0th order Bessel function. Okay. So, these will constitute two counterparts I0 and K0, K0y, and C1 I0 is nothing but lambda r, y is nothing but lambda r. So, I0 lambda r plus C2 K0 lambda r. Okay. This is 0th order Bessel function. This is modified Bessel function. Okay. This is modified Bessel equation. This is modified Bessel equation, or this is not second kind. This is of 0th order. This is 0th order modified Bessel function of first kind, and K0 is known as 0th order modified Bessel function of second kind. Okay. Now, these are basically some functions. These functions can be expressed in terms of sine functions, combination of sine and cosine functions. These functions can be expressed as a summation series. Okay. And they will be having some typical properties. Now, these equation must be satisfying the boundary condition of the original problem. That means, at small r equal to 0, your capital R should be bounded, and small r equal to 1, your capital R should be equal to 0. Put the boundary conditions. At r equal to 0, your r is bounded. So, let us see what is that. Then your r becomes some finite value, let us say it is r finite. Bounded means it will be assuming some finite value. So, this becomes C1 I0 0 plus C2 K0 0, right. Now, this function K0 will be having a typical property. The K0 varies something like this. If you plot K0 by lambda or something, so this starts from very small, very high values at r equal. That means, K0 is infinite at r equal to 0. It starts from the negative minus infinity. So, it becomes infinite. Okay. So, that means, the finite value or the boundedness of the boundary condition at r equal to 0 is violated if this constant is not equal to 0. That means, the associated constant is equal to 0. Okay. Now, r becomes C1 I0 lambda r. This means that, okay. Now, at r is equal to 1, your capital R is equal to 0. That was the temperature is equal to 0 on the surface. That was the original boundary condition. So, 0 is equal to C1 I0 lambda r. Lambda r equal to 1, that is lambda. Okay. Now, this will be having a finite value. This will be having finite value of full domain of r from 0 to 1. Okay. So, that means, these will be not equal to 0.
What is I0?
I0 is a modified Bessel 0th order modified Bessel function of the first kind. K0 is of the second kind, I0 is of the first kind, and these are all given in the either in the summation series or as a combined function of sine and cosine functions. Okay. So, I0 cannot be 0 for this case. That means, C1 will be equal to 0. If C1 is equal to 0, then your whole solution becomes 0. So, again you will be landing a trivial solution. Okay. So, that constant cannot be positive as well. Now, let us look into the third case. Case number 3, that will be this constant is negative. Let us say minus lambda square. Okay. So, in that case, d dr r dr plus lambda square r is equal to 0, that is the governing equation of r varying part, and you put y is equal to lambda r again, and what you will be getting is y d2r dr square plus dr plus yr is equal to 0. Now, you just compare this equation of the with the previous one. This is plus here and this sign was minus there. This is the Bessel function. Right, correct. Of zeroth order, this is zeroth order Bessel function. Okay, this constitutes the solution of the Bessel function of J0, zeroth order Bessel functions J0 and Y0. If this is minus, this is constituted by the Bessel functions I0 and K0, in this case J0 and Y0. Okay, so the solution becomes C1 J0 lambda r, y is lambda r, plus C2 Y0 lambda r. Okay, and now we should look into the properties of J0 and lambda Y0. If you plot J0, let us say J0 versus r, it starts from some finite value at r equal to 0 and oscillates along the x axis, in this case r axis. Magnitude decreases as you go along r. If you look into the variation of y0 and r, this starts from negative infinity, it sharply increases, then shows an oscillatory behavior about the r axis exactly like J0. Okay. So, again this is undefined or unbounded at r is equal to 0. That means, whenever you will be applying the boundary condition that r equal to 0, your capital R is equal to bounded, the associated constant with y0 will vanish. So, your solution, I am not writing it down, I am just skipping the step. So, the solution becomes C1 J0 lambda r. Now, at r equal to smaller equal to 1, your r is equal to 0, that means C1 J0 lambda is equal to 0. Okay. So, J0 lambda must be equal to 0 for non-zero constant to get a non-trivial solution, right. And if you look into the variation of J0 and r, if you plot J0 versus lambda, it will cut infinite number of times the lambda axis. So, you will be getting again infinite number of roots for J0 lambda is equal to 0. Now, again there are typical subroutines are available, which will give for the various values of lambda, you can get all the roots of lambda numerically. This cannot be done analytically, okay. Like the sine functions, cosine functions, we did the things analytically, but for the if you remember the mixed boundary condition, it is again a transcendental equation where the eigenvalues are not found out analytically. So, you can consider it is a transcendental equation. So, eigenvalues of this problem are roots of this transcendental equation J0 lambda is equal to 0. Okay. So, lambda n is, let us say, nth eigenvalue and n starts from 1 to infinity. So, corresponding eigenfunctions are Rn. Rn is C1 J0 lambda n r. Okay. Corresponding eigenfunctions is R a subscript n. So, it is C1 J0 lambda n r. Okay. So, now you can go back to your time varying part for the corresponding for the corresponding nth eigenvalue, that will be nothing but C2 exponential minus lambda n square t, C2 or some constant. Okay. So, your complete solution becomes un is multiplication of Tn into Rn, this becomes Cn exponential minus lambda n square T J0 lambda n R. Okay. So, you use the principle of linear superposition. So, U becomes summation of all the solutions. So, this becomes C1 exponential minus lambda n square T J0 lambda n R. Now, again this constant can be evaluated from the initial condition, non-zero initial condition. What is the initial condition? If you remember, at time t equal to 0, your U was is equal to some function of R or constant, some prescribed function of R or constant. So, if you can put that, let us say this f R may be constant or some prescribed function. Let us say it may be R, it may be 1 minus R square, it may be 1 minus R, it may be R square plus 2 plus 3 R, whatever. So, this becomes summation Cn J0 lambda n R. Now, the constant, now if you remember in the previous cases, the ultimate constant, the final constant of the solution was evaluated by using the orthogonal property of the eigenfunctions. Now, in this case, the Bessel functions are orthogonal to each other with respect to weight function R. So, you can easily prove that. So, if the Bessel function, if you can really prove that Bessel functions are orthogonal to each other, then you can multiply both sides by J0 lambda m R dr. With respect to R means there will be a weight function R in the, okay. The statement is Bessel functions are orthogonal to each other with respect to some weight function R. This means J0 lambda n R J0 lambda m R R dr is equal to 0 from the domain of R, that is 0 to 1, if n not equal to m. This equation, this statement mathematically is expressed like this. Now, if you remember the sine function and cosine functions, the sine functions and cosine functions are orthogonal to each other with respect to weight function 1, right. If you remember, sine function and cosine functions are orthogonal to each other with respect to weight function 1. In this case, in the cylindrical polar coordinate, the Bessel functions are orthogonal to each other with respect to weight function R. This is very simple, you can prove this point. Okay, you can prove this point, it is very easy. The proof goes like this, you just write down the equation of the Bessel function. Okay. What is that? ddr of R dr is equal to minus lambda square RR, right. Now, let us say for we are having two distinct eigenvalues, lambda m and lambda n. Lambda m and lambda n are two distinct. Distinct means n not equal to m. Identical means n is equal to m. Okay, we consider lambda m and lambda n are two distinct eigenvalues. Corresponding eigenfunctions are what? J0 lambda m R and J0 lambda n R, right. Okay. So, R will be assuming J0 lambda m R when lambda becomes lambda m. R will be assuming J0 lambda n R when lambda is equal to lambda n. Okay. Write down these two equations. So, lambda m and corresponding to lambda m and lambda n eigenvalues, you are having eigenfunctions J0 lambda m R and J0 lambda n R, right. So, substitute in the governing equation ddr of R d j0 lambda m r dr is equal to minus lambda m square r r. This r is basically j0 lambda m r. Agreed? Now we write down the same equation corresponding to nth eigenvalue. What is that? d dr of r d j0 lambda n r dr is equal to minus lambda n square r j0 lambda n r. Okay. Let us say this is equation number 1 and this is equation number 2. You multiply the first equation by j0 lambda n r, the other eigenfunction. You multiply the second equation by the other eigenfunction. Here eigenfunction is j0 lambda n r. You multiply this equation by j0 lambda m r, and let us see what you get. Let us do one by one. We multiply this equation with the other eigenfunction, that is j0 lambda n r. j0 lambda n r r d j0 lambda m r dr, okay, minus lambda m square r j0 lambda m r j0 lambda n r, and dr and integrate, multiply both sides by dr and integrate on the domain of r from 0 to 1. That means effectively we are multiplying both sides by integral j0 lambda n r dr. Multiply both sides by dr and integrate over the domain of r from 0 to 1. Okay. Now you integrate this one by parts. This will be inside, right? This r will be inside. d dr of r of that thing. So dy dr is missing. Yes, this is correct. Okay. So you do this by integration by parts. This is the first function. This is the second function. First function integral of the second function. There too is cylindrical coordinates. This is the governing equation of the Bessel function, d dr of r dr dr. So corresponding to lambda m, we will be having a capital R is equal to j0 lambda m r. Corresponding to lambda n, it will be having j0 lambda n r. Okay. Now we integrate it by parts. First function integral of the second function, j0 lambda n r. Integral of the second function is nothing but r j0 prime, d dr is j0 prime lambda m r 0 to 1, right, minus integral 0 to 1 differential of the first function, that means j0 prime lambda n r, integral of the second function, that is r j0 prime lambda m r, okay, is equal to minus lambda m is being a constant, it is not a function of r. So it will be coming out 0 to 1 r j0 lambda m r j0 lambda n r dr. Do you agree with this step? Right? The first function integral of the second function, the prime I am denoting d dr, derivative of that with respect to r. The first function integral of the second function minus differential of the first function integral of the second function. That means this whole term will be appearing there. Okay. Now you put the limits. When you put the lower limits, this whole term will vanish because r equal to 0. When you put the upper limits, you do not have any idea of j0 prime, but what is j0 lambda n? j0 lambda n is equal to 0, because that is the transcendental governing equation for eigenvalues. So the whole of this is known as bilinear concomitant anyway. So, the whole of this term will vanish at r equal to 1 as well as r equal to 0. R equal to 0 there is absolutely no problem, because of the r equal to 0 will be equal to 0. At r equal to 1, J0 lambda n will be equal to 0, because that is the transcendental equation or governing equation to evaluate the eigenvalues, right. So, whole of this bilinear concomitant will vanish, fine. So, you will be getting minus J0 prime lambda n r, J0 prime lambda m r, r dr is equal to minus lambda m square 0 to 1 r J0 lambda m r J0 lambda n r dr. I am writing this equation again, only this term will be is equal to 0. Okay. Now, you multiply this equation by J0 lambda m r dr and integrate from over the domain 0 to 1, and what will be getting? You will be getting, again you will be getting something like this, minus 0 to 1 J0 prime lambda n r J0 prime lambda m r r dr, again this term will be remaining same, only the order will be different. So, a into b is basically b into a, does not matter, is equal to minus lambda n square of the same thing, okay. Then subtract. From equation number 2, what you will be getting? You will be getting minus 0 to 1 J0 prime lambda n r J0 prime lambda m r r dr is equal to minus lambda n square 0 to 1 r J0 lambda m r J0 lambda n r dr. Let us say this is equation number 4 and the previous one is equation number 3. This one, let us say this is equation number 3. Now, subtract 3 from 4 or vice versa, it does not matter. So, let us say 3 minus 4. The whole left hand side of both the equations are same, they will vanish, right. So, it becomes 0 lambda n square minus lambda m square 0 to 1 J0 lambda m r J0 lambda n r r dr, right. The left hand side of both the equations are identical, so they will just vanish. Now, we have assumed lambda n and lambda m are two distinct eigenvalues, that means lambda n is not equal to lambda n. That means, to hold this equation good, this integral must go off, right. So, this indicates J0 lambda m r J0 lambda n r r dr 0 to 1 is equal to 0. That means, the Bessel functions are orthogonal to each other with respect to the weight function r. So, our point is proved. Now, using this orthogonal property, now you can evaluate the ultimate constant Cn that is appearing in your equation. Now, let us look into that equation. The equation of the final constant becomes summation Cn J0 lambda n r. Now, I will be multiplying both sides by J0 lambda m r r dr and integrate from 0 to 1. So, 0 to 1 Fr J0 lambda m r r dr Cn J0 lambda n r J0 lambda m r r dr 0 to 1. Okay. Now, we open up this summation series, all the terms will vanish because of the orthogonal property of the Bessel functions, and apart from one term, that is n equal to m. So, this becomes J0 square 0 to 1 J0 square, let us say lambda n r r dr. Agreed? Cn will be there. So, So, Cn will be nothing but 0 to 1 Fr J0 lambda m r r dr 0 to 1 J0 square lambda n r r dr, right. Now, you look into the Kreyszig or any other book, these integrals of 0th order Bessel function or nth order Bessel function are all given in the in terms of summation series or in other terms, right, like 0 to 1 J0 square lambda n r, this should be lambda 0. No, that is fine, J0 fine. All r will be given in terms of J1, J2 or there are what do you call, there are sequence of Bessel functions, those are available, as well as the integrals are also available in terms of J0, J1, J2, so on and so forth. Okay. So, you can write a compact notation, in compact notation you can write down the solution of Cn, but whenever you will be evaluating the temperature as a function of r and t, you cannot do it analytically like the sine functions or cosine functions, because the complex forms of the Bessel functions, they are all infinite summation series. So, all these calculations has to be done numerically, means evaluations of Bessel functions will be done numerically. The compact form of the solution can be available in a compact notation in front of you, that is almost equivalent to an analytical solution. But whenever you would like to compute something using Bessel function, you have to take recourse to the numerical methods, or you have to take recourse to the mathematical tables that is available at the in the appendix of any standard mathematical textbook, like error functions for different values of x, what are there are tables available, right, tables of error function, tables of Bessel functions, so on and so forth. Either use the table, nowadays nobody uses the table because the solution becomes available numerically. You just add that subroutine in your solution scheme and get the values numerically. Okay. So, Bessel functions will appear whenever you will be working in the cylindrical polar coordinate. Okay. Now we will be looking into one more problem, that is the transient heat conduction in 2-dimensional polar coordinate. Now, in the previous example, it was heat conduction in transient heat conduction in 1-dimensional coordinate. So, it is basically 2-dimensional problem. Now, it has become the 3-dimensional problem. Okay. The governing equation of temperature, you can write it as del u del t is 1 over r del r of r del u del r plus 1 over r square del square u del theta square. We can assume the z dimension is too long and all the variations in z direction will be neglected. Now, again this u is basically your transform temperature, and there will be a constant appearing here, that will be alpha by that is thermal diffusivity, right, alpha. So, let us consider it as 1, it really does not matter, it will be incorporated in the time varying part. Okay. Now, let us look into the boundary condition and initial condition. The initial condition will be at t equal to 0, your u is, it can be some function of r and theta, it can be function of r only, it can be function of theta only, it can be equal to some constant as well. Okay. Prescribed function, whatever the form, it will be a prescribed form, and at r equal to 0, that is at the central line, your u is finite, the physical boundary condition that we have just discussed. At r equal to 1, let us say it is a constant boundary, constant temperature condition, so u is equal to 0. Okay. Now, we have to fix the boundary condition on theta. Now, the boundary condition of theta are like this: u r theta is equal to pi will be is equal to u r theta is equal to minus pi and t del u del theta r theta equal to pi is equal to del u del theta, theta is equal to minus pi t. These are known as the periodic boundary condition. This says that the temperature is equal at theta equal to pi and theta equal to minus pi. That means they are periodic at theta. The gradient of temperature is periodic at theta. This simply means that. In fact, how these boundary conditions come, they are exactly come from the physics of the system. Again, these are the physical boundary condition exactly like this: u is equal to finite, r equal to 0. Because you do not know the value of u at r equal to at theta equal to pi or theta equal to minus pi, but it is from the governing equation, or if you look into the solution, you can find out that they are periodic at theta. So they are purely physical boundary conditions. Again, if someone is interested to know more about this, you can look into any advanced textbook on on physics, where they have discussed the several types of problems like this. Okay. So just for the time being, we take it as granted that these are the periodic boundary conditions, and they are just coming purely from the physics of the problem, and they fall in the category of the physical boundary conditions like this. Now, again we can solve this problem by using separation of variable. One will be the r varying part, another will be the theta varying part, another will be the time varying part. Okay. Now, if you substitute, it becomes 1 by t. If you substitute this in a governing equation, it becomes 1 by t dt dt, 1 by r ddr r dr plus 1 over r square theta hat d square theta d theta square. Okay. Now, change over the side, 1 by t dt dt minus 1 over r ddr r dr 1 by theta hat d square theta hat d theta square is equal to constant. We pose the eigenvalue problem in the theta direction because the boundary conditions in the theta are homogeneous. If you look into the boundary conditions on theta, both the boundary conditions on theta are homogeneous. So, we will pose an eigenvalue problem in the theta direction only, exactly like the previous case we have discussed. Okay. Now, again this constant can be positive, negative and 0. Positive and negative they will be ruled out, positive and 0 they will be ruled out because they will be giving a trivial solution. So, this has to be negative. Now, you just there will be one more trick there. Now, suppose, so basically you have to pose an eigenvalue problem in theta direction as you have homogeneous boundary condition in theta direction. Okay. Now, this constant can be 0, can be positive or negative. Now, let us consider this constant is 0. Let us say constant is equal to 0. So, it will becomes d square theta hat d theta square is equal to 0, right. That means, your theta hat is c1 theta plus c2, right. With the conditions u or your theta hat must be satisfying the boundary conditions on theta of the original problem. That means, theta hat at pi is equal to theta hat at minus pi, theta hat prime at pi is equal to theta hat prime at minus pi. Okay. Now, if you use all these boundary conditions, you will be getting C1 is equal to 0. If C1 is equal to 0, your theta hat becomes C2. Okay. Now, C2 is a non-zero constant. You can utilize both the boundary condition and finally conclude that theta hat is equal to C2. So, that means 0 is an eigenvalue and constant is an eigenfunction for this problem. unlike the previous problems. So, we cannot omit 0 of, as the eigenvalue in this case. So, 0 is the eigenvalue and C2 is corresponding eigenfunction. The eigenfunction may be constant, it really does not matter. Okay. So, that is the case for constant equal to 0. If the constant is positive, you will be getting a trivial solution. You can try that out. If the constant is positive, you will be getting a trivial solution. So, we will not be considering that. If the constant is negative, that is, let us say minus alpha square, that is what you get. You will be getting 1 by theta hat d square theta hat d theta square plus alpha square is equal to 0, or d square theta hat d theta square plus alpha square theta hat equal to 0, right. So, what is the solution? The solution is, let us say C1 you have used C3 sin alpha theta plus C4 cosine alpha theta, right. Now, use the boundary condition that theta hat at pi is equal to theta hat at minus pi. Now, if you do that, what you will be getting is 2 C3 sin alpha pi is equal to 0. Use the other boundary condition, that is the theta hat prime at pi is equal to theta hat prime at minus pi. Okay. So, what you will be getting? You will be getting twice C4 sin alpha prime alpha pi is equal to 0. For a non-trivial solution, that means when C3 and C4 not equal to 0, from both the cases you will be getting sin alpha pi is equal to 0, right. That means alpha is equal to n, alpha pi is equal, sin alpha pi is equal to 0 means alpha pi is equal to n pi. So, alpha is equal to n, where n runs from 1 to infinity. Okay. So, what is the corresponding eigenfunction? So, in this case the corresponding eigenvalues are n running from 1 to infinity, and corresponding eigenfunctions are C3 sin n theta plus C4 cosine n theta. Alpha becomes n, theta hat becomes C3 sin n theta plus C4 cosine n theta when n runs from 1 to infinity. Now, if n becomes 0, let us see, if n becomes 0, these terms will be off and theta hat becomes C4, a constant. So, if I write down n runs from 0, 1 to infinity, I will be including that case as well when my constant was equal to 0. Are you getting my point? Now, this can be a generalized eigenfunction for this particular problem in the theta direction if I state n equal to 0 to infinity, including 0, 0, 1, 2, 3, 4 up to infinity, because at n equal to 0 you will be getting theta hat equal to constant, that includes the case when constant was equal to 0. Okay. So, anyway, the solution is still long, and we will be solving this problem in the next class. Thank you very much.
So, we are going to start with equations of change or conceptual derivation of equations of change for a non-isothermal system. What we have seen so far is it is easy to formulate a problem based on a shell heat balance by considering all the terms, for example, convective terms, conductive terms, through which energy, net energy is added to the system, and equating it to the accumulation of energy in the system, or at steady state that would be equal to 0. What we have seen for the case of momentum balance as well, this concept cannot be used for situations where the geometry is complex, or more than one phenomena is taking place, and sometimes it would be better, like Navier-Stokes equation, if we have an equation which we can start with, that is the most general form of energy equation, and start cancelling the terms as we have done before for the case of momentum transfer, and an equation which takes care of all the effects that are possible that can be there when there is a temperature change in the system. Now, temperature change in the system can be a direct result of net heat being added to the system. When we think of net heat being added to the system, there are two mechanisms which we are considering right now. One is convective, which is due to the flow. So, any fluid packet which is coming into the control volume carries with it some amount of internal energy, which is represented by its temperature, and some amount of kinetic energy. So, it may very well be possible that inside the control volume itself, some amount of kinetic energy is converted to internal energy, giving rise to a change in temperature. So, Qx has to be multiplied to find out the amount of energy that is coming in through the to the control volume. Qx should be multiplied by del y area, which is del y del z. So, that would give you the amount of energy coming in per unit time to the control volume. Similarly, the conductive heat which is leaving this surface would be equal to Qx evaluated at x plus delta x multiplied by the same area. I have the same thing for y, Qy term, Qy and Qz. So, this can also be evaluated as algebraic sum of heat being added at x, being taken out at x plus delta x, at y, y plus delta y, and at z. So, 6 more terms will appear here, all terms containing either Qx, Qy and Qz multiplied by the proper area. So, if you think carefully, through the introduction of these terms, I am introducing temperature gradient. I will repeat my statement again. Through the introduction of Qx, I am introducing the temperature gradient, because Qx is related to temperature gradient by Fourier's law. Okay, so, Qx is simply equal to minus k dt dx. So, introduction of Qx, Qy and Qz essentially brings in the temperature gradient into this equation. Okay. Introduction of this brings in temperature or temperature gradient, which one? Introduction of the convective terms, temperature. Why temperature only? No. But when you are probably confusing with Newton's law of cooling sort of thing. Here we are dealt with rho u plus half rho v square, and u is a function of temperature only. So, we are bringing in the temperature through this, not through Newton's law of cooling, whereas by Fourier's law we are bringing in the temperature gradient in the system. So, what is left is net rate of work done. We are assuming it is by the system on the surrounding, so that everything is going to be negative. And we know that when we have work done, we would like to find out rate of work done. It is nothing but force into velocity. Whatever be the force that is acting on the system has to be multiplied by velocity. So,